Welcome everyone. In this SOLIDWORKS simulation users primer for 3D experience, we will be looking at the analysis of a crank assembly in both SOLIDWORKS and 3D experience. We've covered the basics of meshing. Here we'll look at some additional topics related to meshing, specifically how parts interact with each other, making a rigid body, and the concepts of mesh of assembly and assembly of meshes. So, let's get started. In this particular assembly we have the crank arms connected to the axle, which connects to the pulley. These are all separate components, so have individual meshes. The question then becomes, how do we represent the load path between these components? For loose fit components, this would likely be contact interactions. For this tight fit assembly here, or if we assume something like they are rusted or bonded together, then in the SOLIDWORKS study we can use the default contact interaction, which is set to a bonded mode. So any surface on a part within a tolerance of another part's surface will be bonded together and respond as a single part. In the FEM, there is a similar capability. Changing to the Interactions tab, there is a contact command. This brings up a dialog where we can set contact definitions. The tabs allow options for the initialization and control of the contact, as well as the property assignments. By default, we can see that there is a global assignment, which is active for all and self, and has an analysis default property. That default property is frictionless regular contact, where the contacting objects can separate but can't pass through each other. The all self designation is perhaps new for SOLIDWORKS users. In SOLIDWORKS, all the contact is face pair based. You define a pair of surfaces A and B, then contact is only active between that pair of surfaces. If you need contact between A and C, then a new contact pair needs to be defined for that pair. In this pulley example, the front arm to axle would be a contact pair, the rear arm to axle would be another pair, and the axle to pulley would be another pair. For assemblies with little relative motion and just a few components, this is manageable. For small relative motions with larger assemblies, let's say a factory floor of pulleys, contact detection where pairs of nearby surfaces are automatically found and contacts created is a viable solution. In SOLIDWORKS, this would be the local interactions with automatic finding. This contact pair and automatic detection approach is available in 3D experience as well. But here, in this dialog, we are setting up general contact. In general contact, the user doesn't define which surfaces contact acts on. Instead, during the analysis, the solver detects any surfaces that are coming into contact and then resolves contact on those. This is the all self designation. All surfaces can contact all other surfaces, including contact to themselves, for instance in folding problems. This is much easier to define, not just for small relative motion analyses, but for ones with large relative motion, such as this example of a ball moving into a field of flexible strands. As the ball moves, determining which contact pairs it would impact is effectively impossible before the analysis. Then the possible contact pairs for every strand as they move. Having the solver detect and resolve all the contact is much more practical. In general contact, if you have multiple contact properties, say the ball to strands contact friction is different to that seen in strand to strand contact, then you can define additional contact property assignments and give that a different contact property. This makes even complex analysis interactions relatively simple to set up. General contact is explained more thoroughly in the 3D Experience training material. In this particular analysis though, we don't want frictionless regular contact. We wish to bond these different parts together at their interfaces. In the property drop-down, there is analysis default as well as bond contact. So we can simply swap to this contact property and all the contact interactions will be bonded, keeping the contacting surfaces together during the analysis. This is equivalent to the SOLIDWORKS study global interaction bonded. There are alternative approaches to contact and bonded contact interactions. Things like tie and coupling as well as fasteners, as well as other connections in the connection tower. Some of these will be new concepts to SOLIDWORKS users and some will be similar to connections you are familiar with from studies. However, for initially touching surfaces, there is another option in 3D Experience that I have not seen in SOLIDWORKS study. Mesh capture, i.e. when meshing a component, capture the mesh from an adjacent component and use that at the interface. So we end up with an element on component A, a shared node at the interface, and then an element on component B. This direct connection of finite elements means that this interface is fully connected without any need for additional connections or interactions. To illustrate this, we will return to the Setup tab. There we will duplicate this FEM. This brings a dialog where we can specify a prefix for the duplicated FEM. So here we will say mesh capture, and we will duplicate and include any connections. Then we will double click to switch to that FEM. This does have the contact we set up, so we will delete those features. With the mesh displayed, we can see the difference of meshes for each component. Exactly how you would capture meshes can vary. I like to start from smaller interfaces to larger, so the axle will capture the mesh of the pulley. To do this, since we have all meshes already defined, we will edit the axle mesh command. In the capture section, we will enable capture of nodes and mesh edges. This then shows several other entries. For tolerance, we will take 0.1 mm. Apply on means capture meshes from what other components, so here we will specify to just choose the pulley. Mode is then how those captured nodes will be dealt with. Condensation is the mode we want, which will end up with merged nodes from both meshes at this interface. We will also enable project curves, which will project the end curves from the smaller surface of the pulley onto the axle. And this is why I generally like to work from smaller interfaces to larger. Mesh to regenerate the mesh with this additional control, and we can now see that the mesh of the axle does connect directly to the mesh of the pulley at this interface. We can repeat this same approach with the rear arm capturing the axle mesh and the front arm capturing the axle mesh, ending up with a fully connected mesh through all the components of this assembly. Note, in this example, the smaller interface regions happen to be on the larger mesh size components. So the smaller mesh size components grow the element size at the interfaces. We could alleviate this by adding local mesh controls so that the interface a smaller mesh size was used even on the larger mesh size commands, but for this example we will just leave this as is. I'm not going to go through every equivalence in meshing in finite element models between SOLIDWORKS and 3D Experience, but one that can be very useful in nonlinear analysis, particularly of large assembly models, is rigid bodies. Reducing a component to a rigid body can substantially reduce the model size by not having all of the deformable degrees of freedom for that component, thus allowing solver iterations to run faster. And in nonlinear analysis, there can be a lot of iterations to be done as part of the analysis. In SOLIDWORKS, you simply select any part and make it into a rigid body, such as this rear arm, which won't be part of the main load path for the loading we will consider later. So reducing the analysis resources on this part won't impact the solution. In 3D Experience, we can do the same thing. Within the Abstractions tab, there is a rigid body command. Within this stack is also the ability to create analytical rigid surfaces rather than bodies. In the rigid body command, we choose a support. This could be the mesh or the part body geometry that was meshed. Here we'll use the rear arm part body, remembering that we can use the visualization manager to show only the contributing shapes as needed. A rigid body will have a reference point, a location where we can define what might be happening to this rigid body. By default, this will be specify, which would mean we can select a suitable point in the geometry. Here though, we will change to center of mass. If we were creating chains of rigid body components, or using ties or pins to connect them to other flexible components, we could then specify where those connections are on the rigid body. Here we aren't doing that, so we will just leave these as blank default. And now we have a rigid body representation of the rear arm, so computational resources in this area of little interest are minimized. Returning to the top level assembly, we now have 3 finite element model representations. The automated FEM, which was batch meshed, the manually created FEM where we built everything from scratch, and the mesh capture version where we copied the manual FEM, used mesh capture to connect the different geometries, and then made the rear arm rigid. All of these have been mesh of assembly finite element models. There is a single FEM at the top level assembly. Within this FEM there are individual mesh and property commands for each component. Apart from the ability to have multiple finite element model representations, this is very similar to the mesh within a SOLIDWORKS study. However, there is a different way to organize a finite element model, assembly of meshes. To illustrate this, we will open a part individually, here the pulley, which can be done by right-clicking on the part, going to that object, and then choosing Open in New App. This opens just that part and associated features in a new tab. So we see the part, the 3D shape of the original import, and the abstraction shape that was created earlier. We can create a finite element model within this part by inserting a finite element model. We will then also rename this FEM so it's clear what the intent is, and then double clicking it to switch. On first entering the FEM, we again need to select the contributing shape as we have a choice of what to mesh. We will select the abstraction shape here, then we mesh and apply a section as we have before. Now in the assembly we can see that the pulley component has this part level FEM. We could have repeated this for each part in the assembly, but for this example we will stick with this single part. An assembly of mesh FEM is a FEM which assembles other mesh to create the full model. So here we will insert a new FEM in the top level assembly and rename it as appropriate. When we go into this FEM, it will once again prompt for what geometry should be meshed within this FEM. Here we will leave that blank at the moment. Now nothing is displayed because by default in the FEM the display will only show shapes that are contributing to that FEM. This can also be done via the Visibility Manager if your default is different. If you go to the Setup tab, next to the Contributing Shapes command is a Contributing Finite Element Model command. Selecting this brings up a dialog where we can choose what FEMs within this assembly we wish to use within this top level assembly FEM. At the moment, because we only created a part level FEM for the pulley, only this has an option saying one candidate FEM. If we right click on this, we can choose to select that FEM, confirming this, and we can see in the display we do now have this pulley mesh within this top level FEM. This is an assembly of meshes FEM. There are no mesh and property commands within this top level FEM. Instead, those are all defined at the component level and then referenced here in this top level. We will duplicate this FEM to create a hybrid assembly of meshes and mesh of assembly FEM. We will change to this hybrid version. The pulley mesh remains as that is referenced as part of the contributing FEMs. This time though we will also open the contributing shapes and select the abstraction shapes for the arms and the axle. Then we can assign mesh and assign properties to these components as we have before. So this hybrid FEM has aspects of mesh of assembly, the mesh and section features for those components, as well as aspects of assembly of meshes, the pulley part level FEM reference. This can lead to questions as to which way should you, as a particular user, go about meshing in 3D Experience, to which the answer is, it depends. One advantage of assembly of meshes is that if you are dealing with large, complex assemblies where analysis needs to be done on multiple sub-assembly and part levels, then rather than having many different meshes all containing their own mesh commands for the same feature, you can simply reuse the FEM at the different levels. However, the downside is that because each mesh is individual at its own level, they don't tend to have influence from higher or different sub-assembly levels. For instance, we can't capture the mesh from the axle on the pulley in a part level mesh of the pulley because the axle mesh doesn't exist at this level. In this case, it is easier to do this with a single top level assembly mesh because everything is then represented in that top level assembly. And of course, as we've just seen, you can combine these aspects. A single FEM doesn't need to be exclusively assembly of meshes or mesh of assembly. You can mix and match these as needed for your requirements. My personal advice for SOLIDWORKS users familiar with studies would be to initially keep with mesh of assembly. It is closest to the organization from a study, which will help adoption. Once you are comfortable with this, then start experimenting with assembly of meshes where it seems most useful for your analyses. To summarize, finite element models or FEMs can be meshes of assemblies, or assemblies of meshes, or a hybrid between these. And in addition to meshes and sections, other abstractions can be included in a FEM, such as rigid bodies and contact, both regular and bonded modes. Thank you for your attention.